So I'm Vojta, or Vojtech. Usually when speaking in English, I say Vojtech. So I'm the founder of golang.cz. We are a software company, and we are obviously using Go heavily on the backend side. We are also building software applications with React and Svelte on the front-end side. We're very heavy on Kubernetes, Pulumi infrastructure as code, and GCP, AWS, and so on. We are working with customers around the world, most notably right now with Horizon Games, which is building a set of SDKs and APIs, and I would probably call it AWS for blockchain. So we're building like a set of huge APIs that will help game studios to use blockchain very easily. And one of the biggest customers that we onboarded last year is Ubisoft, and they started using the platform for pretty much all of their Web3 games. We're also working on some other projects, and we are also hiring. Shameless plug. So today I wanted to talk about building scalable REST APIs. Building REST APIs, and especially maintaining REST APIs over time, can be very challenging, right? How many of you have built any APIs using Go? Perfect. That's a lot. I love it. So if you want to build and maintain the REST API by hand, that's sort of like the obvious choice when you're starting with Go. You need to write lots of boilerplate, essentially. So first you need to start with creating the server and mounting your routes. So this is the pretty much new syntax since Go 122 for registering multiple routes. As you can see, you can put method in front of the path right now, and then you can pretty much handle that route with a specific method or a function, right? In this case, as you can see, it's a simple CRUD for users. So you can create, update, delete, or list users. And you need to, of course, write all these routes and mount them on top of the HTTP server. Then you need to implement server handlers. So I came up with this like very basic, let's call it an example code. It's not perfect. It might have bugs. But essentially what you need to do when building REST API with JSON, you need to, of course, decode the incoming JSON from the request body. You do it usually with JSON unmarshal or JSON decoder. Then when you unmarshal the data into a runtime struct, you can see the user struct at the top of the file. Then you can do some heavy lifting with the runtime object, right? You can load it from the database, you can validate the data, you can process the data, and then save it to the database. And then you need to return it back to the user, which means that you need to, again, encode it into JSON. So we're using JSON.marshal or JSON encode for that. Of course, when writing APIs that should last long, you need to write your client. So first, you need to write your client in Go, and then second, client in TypeScript or any other language which is important to you or to your customers. So in Go, again, this is a sample code. You need to, for example, this is for accessing the put users method. I just called the client method update user. And again, you have a runtime object, you need to marshal it, you need to create a request, you need to send it over to the server, and then receive the information back from the server and marshal it into your runtime object. And you need to pretty much do this like for every single language, right? That you want your users to use. So this is, for example, TypeScript, but the concept is the same. Lots of marshalling, lots of unmarshalling. And of course, you will need to maintain your API documentation over time if you don't want to have any angry customers. And when you're maintaining REST API for a long time, you need to repeat this process every single time you make any changes to the API. But is there any better way? So today I want to introduce you to WebRPC. WebRPC is a code generation tool heavily inspired by gRPC from Google or Twerp from Twitch TV. A huge difference is that we don't have protofiles and we don't use protobufs. So there's no binary streams, binary data over the network. WebRPC is using JSON format over the network. So it's like very easy to use from the web browsers. It's compatible with all the browsers. It's compatible with all load balancers. You can use Chi middleware, HTTP middleware as with normal REST APIs routes. And there's like some other benefits like that. Instead of protobuf, we have Riddle. Currently, WebRPC supports generating code into Golang, client, and also server. And we also support TypeScript, JavaScript, Kotlin, Dart, and Swagger or OpenAPI. What's cool about WebRPC is that it's a simple Go tool, and it's actually generating all the code using Go templates. And all of it is open source. So if you take a look at any of the templates, you can fork them on GitHub and tweak it and change it to your needs, and then use it using the generation tool. So if you think about this, approach, WebRPC or gRPC, suddenly you don't need to maintain, you don't need to create server routes because the router is actually included inside of this approach. You don't need to write clients anymore. You don't need to write API documentation, and you just simply run a command which does all of that for you for free. All you need to do is maintain the Riddle file or protobuf in case of gRPC, and then adjust the server implementation, the methods. So this is an example of a Riddle file. So you can see that I just defined one object, which is user. You can, of course, nest objects and use more complex fields inside of it. And then we define the service definition. And we have 6 methods defined on this service. And you can notice that it's basically the CRUD that I was showing you before. So we have create user, update user, delete user, list users, etc. And all of it is like, in a pretty simple format in Riddle file. And last but not least, with WebRPC, we are also defining very well-defined schema errors inside of the Riddle file. So what this means is that when you're returning errors to the client, you can actually typecast them from the client side. So you can ask, oh, is this rate limited error? And if it is, then you can, do some exponential backoff or something like that based on the logic that you need. WebRPC also supports streaming. Unlike gRPC, it's only one direction, so it's server to client. We have custom schema errors. We support enums, which is a big pain in the in Go, because we don't have enums in Go. And when you have iota constant, then you need to always create a custom marshal for it. This enum does it for you. You can import riddles inside of riddles. So you can create a structure of your data models. We have method annotations, so you can filter out different things when generating the code. So for example, if you had some internal only endpoints, then you can hide them from the public-facing API client. You can define multiple services inside of a riddle file. A typical example would be that you have admin routes and public routes, or something else, right? And then you can create 2 different clients out of this. So let's take a look at the demo. All right. Sorry, guys. I have this little window here, which is annoying. Okay. So where do I start? I think I will start with the example.riddle file. So this is the schema definition as we just described. On the right side, we have a server which we instantiate, and the server itself has a handler. So let's take a look at the server. So the server can be any struct. You can have configs, database connection, pools, a custom logger, whatever inside of the server. Then we are defining the router, the HTTP handler. In this case, as you can see, you can just use the whole Chi ecosystem inside of these routers, because it's just like an HTTP server. It's nothing special. So you can use all the middlewares that comes with Chi. Most notably, I would say CORS, rate limiter, middlewares, custom request logger, no cache, trace ID for tracing requests between multiple services, or you can just limit let's say the number of minutes that the request can take. And now, as you can see, my server is just implementing what I described in the schema. Now, how does this work? And maybe we should just like modify the code, and let's add a new method. Do you guys have any good ideas for the method name that we want to add? Okay, I'll just use the delete user. Let's delete some user. Perfect. So we need an ID for that, right? Do we need anything else? Just the ID. Let's assume that we are a super admin. Let's go for it. So what I'm going to do right now is run make proto. And this was the tooling. This make proto auto-generated all of the code that is necessary to run the new server and to run all of the clients, and also to run OpenAPI documentation. So as you can see, we have a new method on the client interface, and we have all this boilerplate that I was describing before written for us for free within 200 milliseconds. So I don't need to write any unmarshalling or marshalling code for JSON. And also I don't need to write any routing. Now, how do I use this? So, I have this make file here that I want to show you just just so you guys know what it does. Here it is on the right side. Perfect. So the make file, we have this run tool, which will just rerun the server for us. Then we have some tests. So I can actually spin up the tests against this server. And this proto, which I just ran, is the WebRPC tooling. As you guys can notice, the WebRPC gen tool takes in example.riddle schema, which we defined previously. And then we define a target, which is a Go template behind the scenes. And actually, if you fork any of these templates on GitHub, you can just write them in. So if I did that, I could just use a custom template from GitHub, and it will just work. Also, you can define a local directory. So if you don't want to fork something on public in GitHub, you can download it, you can put it into your code, ideally with Go embed, and then you can just run it inside of your code base. In this case, I am generating Golang client into this client folder. Then I'm generating the server code into the server.gen.go in a current folder. And then I'm also creating a code generation for TypeScript and OpenAPI. Now, let's try to run the server. Ooh, what happened? So we have a new method that we need to implement on our server, right? Let's do it. So now I need to go into my server implementation and create a new function. Yep, that's it. And I'm just gonna return nil. That sounds good. Now, if I rerun my server, it already works. And now I can actually run the tests against it. And I'm gonna do it using make test. So I can see that my server is now receiving some information. For the purpose of this talk, I've also enabled some extra debugging so we can see what the server sees. So this is the request body that my test actually sent over to me. This is a curl, which I can copy and run manually. See, the server is actually responding. And I can also see some headers and some extra information. But the test is failing. Oh, by the way, don't worry about this one, because the test is trying to spin up a server. But if it already exists, it will just print out this error log. So let's take a look at the test itself. This is our test. We instantiate the server, and then we try to listen and serve on the server with standard library. If we cannot, we will just assume that there is a server already running for the purpose of this test. Then we sleep for 500 milliseconds just to make sure that the server is actually up and running. And then we instantiate the client. Here you can see that this is actually, again, a code-generated code from the client subfolder. And we instantiate the client out of it. And then we are running. This is our generated API client, right? So we are just invoking the methods on it. But it's not local. It's actually a JSON communication behind the scenes. So right now, I should be able to delete the user. Sounds good. Let's rerun the test. And looks like it worked. So Now, how do I prove that it actually worked, right? I think we need to go back to the server and let's say that we will want to define some error. And let's use error database down, and let's assume that there was some cause. Let's say this was some underlying database error. Now, when we rerun our test, we can see that it's failing now. And what we are getting back is the database down error. And let me just remind you, this is what we defined in the riddle file. So this is a well-defined error message. And in our tests, but not only in tests, this might be used for service-to-service communication. This can also be used from within TypeScript. So when we are writing TypeScript applications, let's say in React or Svelte or anything else, we can also typecast these errors and see what was the actual cause. So in this test, now I can actually check what was the error. The AI is helping. That's perfect. So if the error is of this type, database error down, I'm just going to print out, oh no. And if I rerun the test, we can see that it worked. So what's really cool about this, we are not only generating code, but we are also code generating errors, and errors that is working not only on the client side, but also on the server side and between the applications. Last but not least, let's take a look at the, okay. I was running it already. Let's take a look at Swagger API documentation. So this is just a Docker container that is running on top of the riddle file that I created, on top of the YAML, which we created using WebRPC code generation. And as you can see, we have the new method in our documentation. And this is ready to go. I can share this with my customers, and they will have always up-to-date documentation for my REST API. But what if I, let's say, deprecate some of this? Let's say we deprecate get user. I don't know why, but maybe it's a good idea to deprecate it. And again, I'm just gonna rerun the tool. I'm gonna rerun Swagger API. And as you can see, it's already deprecated in the inside of the OpenAPI documentation. So I think this concludes our demo. With JSON, we always sort of struggle with its performance. And that's why Google came up with gRPC and the binary protocol, especially for very large or very nested objects. But as of today, there are some good alternatives which you can take a look at. For example, JSONiter is 3 to 4 times faster than the standard library. And Sonic from ByteDance, which is the company behind TikTok, they created a JIT compiler for JSON, which you can use as a drop-in replacement for standard library. And it is blazingly fast. And I was measuring it with just a pure JSON encoding and decoding, and it's like 5 to 10 times faster. So at this speed, you know, it doesn't really matter if you're using gRPC or JSON. we are actually at very comparable speed. Time for questions.